Okay, another version of this type of relative motion problem. Let's say Reed's running north at 6, Meg is 2 meters behind and she's running also north, but at 8. How long does it take Megan to catch up to Reed? Again, I'm not going to try and draw this, but I'll draw it, but I'm not going to try and draw runners. We've got Reed, he's here, he's moving this way at 6. Meg is back here. She's moving this way at 8. It says that there's a space between them of 200 meters, so the 200 would fit in here. You might be able to do this intuitively, but like I said, I'm always going to do the opposite arrow thing. Let's jump into the perspective of Meg. To switch perspective, we add the opposite. Meg's moving at 8, so we're going to 8 north, so we have to add an 8 south to everything. So an 8 south brings that back to 0 as expected, but when we add an 8 onto here, when we add vectors, the answer is always the connection of the very, very start to the very, very end. 6 forward and 8 back leave us with 2 meters per second. This one happens to be pointing south. So from Megan's perspective, she sees Reed 200 meters away, but approaching her at a rate of 2 meters per second. That is kind of math we can do trivially. Is that a word? A trivial math. 200 meters at 2 meters per second means it's going to take 100 seconds. That takes care of the how long. The question didn't ask it, but if we wanted to know where, we now know that Meg goes 8 meters per second for 100 seconds. That means Megan would move 800 meters. Because they were moving in the same direction, when we switch perspective, we end up with a lower overall speed, and then we can just use some logic to figure out the when and the where.